curious, who's actually eating lunch?
Alright, I think this is all we're gonna get. I want Joey to join, but he's not coming. Then I'll send he can watch a video later. So welcome to our third Lunch and Learn. I believe this is probably one of the more interesting one. So to start with, here's the outline. But before I even go to the outline, I want to show you guys a quick video. This is an episode from Mythbuster, co-hosted with NVIDIA. Back in 13 years ago, if you guys remember Adam Savage. He's a YouTuber now, by the way.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions
Turn up the volume?
one after the other.
Did I turn off the volume?
And then could you just turn it up? It's just very quiet.
In 3. All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
when we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target, hopefully. When it's all said and done, it's going to paint the Mona Lisa.
Isn't that the same as the machine?
GPU painting demonstration.
Yep.
In 10,
9,
9,
8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
So yeah, it's a pretty visceral demonstration of the difference between CPU and GPU. That is not to say one's more superior than the other. CPU is more like a tiny race car that you can drive that has very quick ability to turn into corners and then make drastic maneuvers that a larger vehicle couldn't. But the GPU is more like a truck or a chain, right? A freight train that carries tons of cargo at a time, has a pretty hard time turning, but it gets work done a lot faster, especially the same amount of work, right? So the same GPU was invented because people were trying to make games. The game is actually probably the primary driver of the GPU technology, forward shorted by machine learning. They really want to push the boundary of what's possible because they render like millions or even billions of pixels as an operation per frame, and that we do that all like 60 times per second. So it's definitely a huge amount of computation that's required. But then it's wise to keep in mind that the GPU is still programmable, right? Shaders are in short term a program that runs on the GPU. And then you can see that if you have a huge array of data, GPU is basically capable of running some operation on all those elements at the same time. So what GPU is very good at is to say, given an array of 1 million elements and multiply all of them by 2. So that's what some GPU is fairly good at. And that's why, since like matrix multiplication is something that CPU is also very good at, and then they will later on carry it over to become one of the powerhouse of machine learning technologies. But machine learning stuff aside, today we'll be mostly focusing on what GPU, how shaders are used in game development and in Maliang, right? So we have what we see here is a render pipeline. So this is actually, I was having trouble finding a good image representation for that. I think this is the closest one I can get. So you're basically feeding a bunch of geometry data like polygons, right? And then we have a shader that's a vertex shader that computes the projected position of those vertices in screen space, right? So if you have a cube in in your screen. And yeah, so I believe this will all be missing. And then if you were to move your camera around and pan around and look at the object from different, so the same geometry will be projected onto different values.
Are you sharing the wrong screen?
I think I am, sorry. I'm gonna share my entire screen now. So it's gonna look different, and then so that's more of a vertex shader. It kind of translates 3D coordinates into 2D coordinates onto the screen based on the camera and object data. And then that's something called rasterization. Rasterization basically is a scanner. It goes from left and right to detect whether if a pixel belongs to the triangle or not. And then once you figure out which part of the triangle points belong to the triangle, it goes to fragment shader. Fragment shader actually add color onto the pixels on the screen. So this is the long and short of it. So there are two stages roughly. One that deals the vertex information, so that's discrete information. There are millions of polygons on a model often, right? All of those vertices gets computed in some form. And then and once it gets become projected into an area on the screen, it then goes to the fragment shader where it gets colored. You can do more visualization using shaded wireframe mode. You can see that. So you can see this these lines indicates where the triangles are, right? So each of those pixels inside the triangle went through this rasterization process, the fragment shader step. So basically, I just described the two shader, vertex shader and the fragment shader. There's also a full screen shader, so that's mostly used in post-processing. Post-processing shader basically takes the rendered result of the screen and then goes through some additional operation with it. So basically anything. Let's find something interesting. So let's actually press play. And let's find the global volume for it. And then here are all the things you could do with post-processing. For example, Bloom is a very classic example of a post-processing result. So it actually takes the screenshot and then re-render it and then blur it and adds the result on top, so all the plate sets are glowing. Let's actually turn off streak first so it's more obvious. So what Bloom does is that, so like when Unity renders the screen, some pixels are actually brighter than the screen can support, right? It's greater than 255 color. So what it does is that it may renders another image and then have that more cut off and then blur that and then add on top of the original image, so you can have this like blurred outline to simulate the effect. So that's a post-processing shader. It usually applies to the rendered result. So it's fairly close to fragment shader, except the entire screen is two giant triangle. You can think of it like that way. And lastly, we also have compute shader. There's nothing that's limiting GPU to only generate visual stuff, right? You can also do a lot of simulation. You can see this water, how it's flowing, and then how the water is like generating, flowing in real time. That's also computed with a different shader called compute shader. Compute shader, you can imagine, is like a playground that generates data, transform data in whatever way that's applicable. So in this case, like the result is rendered into a separate buffer that represents this water flow that does not go to any part of the image screen directly. I can look away, but the simulation is still being run. Okay, so I want to show you guys what shaders are capable of, and then I'll be walking through how to create some shaders with Unity. So So, quick quiz. Who here has played Assassin's Creed?
Was my favorite game until they created a new one.
Yeah, I pretty much played all of all of the franchise.
So, if you do, you guys remember the Animus loadings?
Oh yeah, like the like you can just walk in the space.
No,
right?
no. I meant by loading effect.
Oh, this one?
That's so cool.
Yeah. You can see like the building kind of gets structured from bottom up, right?
Yeah.
It looks like that. And then that's basically kind of what I did with when I was doing my lunch learn. I was thinking, what's the cool thing that I can build with Shader?
This one's cool. Very cool.
These are things that are not touched by the shader, but yeah, I kind of recreate the Animus loading screen. And that's what I'll be showing you guys how to build today.
Okay, so is this post-processing or is this
It obviously wouldn't be post-processing, right? Because we're actually distorting the geometry.
so what kind of shader was it you count this as?
What do you think?
I'm not quite.
Okay, just
So
think,
it-
where do you think this distortion happens in this these steps?
You're working, going directly on the vertex, right?
Yeah, so it is actually a vertex shader effect.
Oh, okay. Oh,
You can see like when they're far away, it basically all the geometry get flattened into one single layer. But
Yeah.
as I drag it out, like things slowly gets pulled back, and it's all relative to the camera as well.
interesting. So technically speaking, you can generate like 3D model, procedural generate 3D models.
That's what geometry shader is. That's a
Okay.
real thing.
Mhm.
Tessellation is usually used by like when you have a large flat surface and then you want to add more details. You can have GPU to dynamically further create triangles with a given geometry. So that's a tessellation. It's a separate shader. That's actually one of the pre-predecessor of nanite, right? Like it's the technology built on top. It's an adaptive way to add additional geometry into existing geometry. So if the object's further away from the camera, it actually adds less geometry. But that's a sidetrack. So the first thing I want to do is kind of create like a glitchy shader. So for us to do that, the first thing we want to do, let's start brand new, right? Let's just start with some empty scene. The club seems fairly empty, so let's go to the club. So let's create a billboard. And then the first thing we want to do is probably kind of make it emissive. So you'll probably create a material, and then I will create a I'll make it emissive. And I'll select image to be my ad. So there it is, fairly straightforward. Let me just also add some light so it's not too boring. Okay, so a common effect that for example, the effect we want to create, let's call it, the thing let's call it is a chromatic aberration. This happens because the light bands differently depend on wavelengths actually. But like, let's say I want to just to split up the channels, so create this like trippy glitchy look with the separate RGB channels, and then I can create kind of like a broken ad display. So the first thing I want to do is to create a new shader, HDRB. We use lit one by default. Let's call it glitchy ad. So in this glitch ad, you still want to supplement probably two things. So the first thing will be the texture, and then that texture will probably go to directly to emission. But let's also add a intensity. So let's just replicate the basic shader. So the emission is basically a color value, right? And then intensity, we just need to multiply these together. Wait, what can I do? Okay, I have to sample first. I can multiply this intensity value, connect to the output. Let's also set the default value to 1 to have sensible defaults. And then here I will change the shader, glitching add. Here I'll select the texture again. And then I can increase the intensity, so get back to where we are. So we're pretty good, right? So so we're gonna be working with like a material shader for this one, meaning that we're not gonna touch the vertex part, we're only gonna touch a fragment part. So we're not gonna be distorting geometry in any way. So for one important thing to know is look at a sample texture 2D. Sample texture basically takes the given this image, the GPU at a given point has to go to the image and find the respective color on that image, and then they do that for every single pixel on the screen, and that's how I was able to find it. So if you were to distort this UV, you will be able to shift the image by a bit. So let's create another one value called UV shift to demonstrate. Let's add together. And then we'll have the UV channel here. Now this will allow me to adjust the UV to create almost like a scrolling ad, because it's indexing different value on the image. But one interesting thing you probably already noticed that this actually shader, when I did the example, it actually allows me to split into different channels, right? So I could make it so that I'm only using the green channel. Then the image will just become black and white, and then the intensity color will just come from the green channel. So what we could do is to sample the image 3 different times. We'll copy that, paste it here. And then for this channel, we won't do any shift. And then we want to use the green channel for this, and we can combine image together. And then we'll do it again. And this one, I wouldn't do a add, I'll do a subtract. And then I'll recombine the blue channel back in here. So what this allows me to do is I would to drag this value. I'm actually indexing, sampling the red, green, and blue channel at different places. So imagine if I were to just write a script to animate this value, I create a nice glitchy effect. I can do the same thing versus vertical axis as well. So that's a very simple chromatic glitching effect. Now, let's go back to look at the one we did for the. Actually, before I do that, let me just quickly show some of the other shader that we have been making for this project. One of the more interesting one is the steam room. I don't know how you guys can clearly see this, but you can see that there's actually water droplets like slowly dripping down, and then they actually distort and then blur the background image differently. I could actually, let me just increase the speed for a bit. You can see the start dripping. So this is kind of like the ring / steam effect. How this is done is actually Unity allows you, HDRB at least, allows you to not necessarily render the color, but allow you to calculate things like distortion and distortion blur, meaning that when this material gets rendered, you will then be able to distort / blur the image behind it. So it's kind of like a filter that's played on top. So there's a lot of things there's a lot more interesting you can do with. In fact, HDRB do not directly write into color, right? Because it kind of writes it. If you look at the output, it writes with the base color normal. It also actually writes metallic, emission, smoothness, so etc. So what happens is that the game actually goes through multiple stages of rendering. It renders the metallic emission information and then does a pass to combine all the information together. This is very helpful, right? Because you don't have to figure out how the mass of smoothness, metallic, etc., what their impact is going to be directly onto the final color. You just have to think about the physical property and how you can tune it. So now back to this shader that we have created for the animus effect. This is a huge mess, to be frankly, because I admit it, because I only took me only half an hour. I couldn't have time to optimize it. But that also shows like the strengths and weaknesses of shader graph. Shader graph is fairly easy to get started, but if you want to do any sort of complicated math, it becomes pretty chaotic pretty quickly. So generally, it is advised that you it's advised that if you have anything that involves more complicated math, you use a custom node that you can program directly inside the shader. So how this is done? So I was basically observing the animus effect, and then my hypothesis was that there's obviously glitching around, etc. But I more care about how the buildings are slowly being constructed. So a good thing, often thing I do is I would in YouTube you can do the comma and period that step over frame by frame. One of my observation is that the individual mesh geometry, they actually kind of stay the same with the base, but the horizontal, but in vertically the axis get scaled. So my hypothesis that how it probably works is that the further, so if it's within a certain distance, if any given vertex, if it's close to the camera, you wouldn't get distorted. But once it hits a particular threshold, it will basically getting collapsed. So the further away it is from the camera, the more distortion you will have, and then the distortion is basically getting close to zero. So you basically end up with a very simple graph that looks something like this. So you have the distance to the camera, and then this y-axis is the y scale factor, right? So if it's 1, the object did not get distorted. So basically what my shader does is that it keeps 1 as long as it's close to the camera, but once a certain threshold, it starts dropping down until it hits 0. kind of so its function look like this. So now knowing that this will be the range, like I guess start. So basically, how far it is from the camera will the distortion happen, and this will be the range. So how far does it take for it to fall off, right? So the mask become, so you basically just have to write a function that approximates this, which is fairly straightforward to do. And then you can also write some code that tune it, and then it's working as expected. So if it's like, so basically here I'm saying like if a pixel is like too distance away from the camera, you will not suffer, but otherwise you will collapse over the range of like 3. And that did it perfect, and then that worked out fantastically. Some other example of how we so like shader does not necessarily always have to be like making super fancy stuff. There are ways that you can use a shader that just create more realistic looking effects. Example that I will give is the I guess like the shader blending. So if you have 2 different materials, right, you can actually blend across one version to another. That's kind of how they create rust. So let me actually try to do that. So this will basically allow this texture. I'm actually going to create a, I'm going to just be reusing this one. This will allow me to blend across 2 different textures given the mask. Let's just call it A and B. So there's also a lot of noise that you can, there's a lot of noise node that you can have that's built in shader graph. Noise is also pretty cheap because it's basically a deterministic function that takes in the UV coordinate and outputs a color. This is generally cheaper than to use a texture to represent this because texture you actually have load that memory into GPU. So we can just use the value of the gradient to kind of do a lerp. So we'll do an add node. So we will add the noise, the value, and then the shadow together. And then we can already kind of tune it to see what would that do to the mask image. But yeah, we also probably want to clear the result to go from 0 to 1. So what this allows me to do is to adjust this to go from completely black to completely white. And then we can then use this to kind of mix these 2 textures together. So what this allows to do could be creating some sort of rust effect. Let's find some metal. Select the gold texture. And then, okay, let's say the shadow is go to the negative one first. So it's 100% this color. And then for this one, we'll have some sort of yeah, no, I'm just gonna choose a random color texture. Actually, let's make it probably more interesting. Some actual pattern on it, so you can see more obvious what this guy's doing, right? So by creating the dragging the shadow, we're kind of creating a transition between the 2 effects. And then because we added a clamp node, it's going to be pretty easy for us to like it wouldn't go on create strange looking effects. So you can imagine if you can have a bloody, you can have a character or so like there's a lot of you can create right just by blending two textures, right? You can create rust on some metallic surface. You can kind of create a transition between a young skin into an old skin by mixing shader together. So there's definitely a lot of potential, and then there are people's whole job in RJ Studio is to create interesting shader for in service of gameplay and also for visual for visual direction. Okay, so that's what I want to share today. So I basically share how to create some basic shader effect with shader graph, and then but I also kind of reproducing what kind of existing shader is out there. Yeah, and then I would just, and also there are also cases that it's maybe not so straightforward that one shader can take care of it, right? So this effect, when open the, I'm gonna use the slow mode so you can see better. Can anybody tell where I got the inspiration of that effect from? It's a fairly old game, so you may not know. No guesses? It's actually the Protoss dialogue scene from StarCraft 2. I'll show you. That guy.
Oh, StarCraft 2. That's becoming an old game now, eh?
It's a pretty ancient game now these days. But yeah, so like this effect is actually a multi-layered approach, right? So, so when I started the effect, like I'm actually see if I can do like a frame over frame. So you can see that I'm actually distorting this image differently, and it's actually different segments over the background. And in addition to that, I also added some blue streaks that kind of scrolls up on top. Again, that's also animated. So this is what you're gonna have be basically running into when you are creating any sort of a cool looking shader effect. It's often the result of multiple effects in combination and in harmony with each other. Definitely requires a lot of experimentation. So if you want to try to create something, try to keep the individual shader simple, so it's obvious what it's doing, and then be more smart about how to string those effects together. Okay, so that's the presentation part of the shader. I'll be and it's like just over half an hour, which is great. This is the time I'm expecting. I'll be taking questions, or maybe there's some interesting effect you saw and then you want me to look into how to reproduce that. I can give you some idea. This is also might be useful for people working on Malayang later, just because that syncing in GPU parallelization is a good way to think about how to do the image processing side as well, right? Like if you are working, for example, like if you want to flip the image, like invert the image, obviously you could be trying to find some library that does it, but what if you want to create some very specific effect, run some particular conversion? Might be a good idea to see if whatever language or framework you use have some sort of integration with CPU, so you can write some shader instead. All right, any questions?
I have one.
Yeah.
So what's the performance cost of shaders? Is there, I mean, they're probably different from things to different, but what's general? Are there any good rules of thumb for performance?
Yes. Generally, you want to avoid branching, right? So, so how GPU they also does like branch prediction, all that. So what happens was that if you were to write some code like if else, right? Let's say if you do like a color dot alpha equals to less than 0.5, you do blah blah blah. If color dot if you do an else branch, you do something. In CPU, it probably doesn't really care because only one thread is going in. But in GPU, there's like hundreds of threads or thousands of threads going on at the same time, right? And then what ended up happening that if the GPU have to do a lot of branching in adjacent data, basically each so GPU divide the work into different thread group, right? So a thread will contains like 4,000 processes, and all 4,000 processes has to complete at the same time, so they'll be waiting on each other. So if let's say this branch takes like 400 cycles, and this branch takes like 2 cycles, if they happen to be in the same thread group, all of them will not return until 400 cycles. So data locality is also still very important in GPU data. How would that translate to this, right? So GPU, when they render this image, they also kind of divide into groups, right? Let's say if you try to make the effect, so if the color is white, you will do some fancy operation, and then if it's black, then you wouldn't do much. But if your image is looking like this, what the fuck? What? Anyways, so if your image is like half black, half white like this, then it's not too bad, right? Because the GPU kind of divide the calculation into like different groups, and each group is like a square of pixels. So all of this, as long as they are following the same branching, it's okay. But if you have a if you have a lot of if you have texture that's like very noisy, right? Then it means that like the individual pixel going from left and right in the shader block, they're all doing very different things, and that's when system can really slow down. So if you run into something like this, and if you're trying to drastically things different, try to go back to sync if there's a way to kind of do it smart, and then kind of so like but again, like if you're looking at this particular example, if you just follow the general principle of data locality and uniformity, that's gonna help your GPU. It's also gonna help your CPU, by the way, right? Because CPU also has to do a lot of branch prediction. If you try to have GPU do the same thing in a loop of 10,000, it's gonna be pretty fast. But if you in the CPU, if you do the loop in every other loop, it does something different, the branch prediction will fail, and then it has to rewind back to the pipeline and do it again. So yeah, GPU is not that different. So if it's just like it really exaggerates the effect because there are so many things going on in parallel. It's a good question. It's also another unfortunate thing with shader is that the shader performance is generally pretty difficult to evaluate. Unlike CPU, there are profiler. It kind of tells you where the CPU is spending time on. Commercial PC hardware generally do not have a profile available. You can, however, like set a debugger on like a PS5 or Xbox, but most people don't really have access to development hardware like that. And then just because you optimize your shader for Xbox hardware doesn't necessarily the performance will transfer back to a PC. Often it will, because the principle is similar, right? Like also, like Xbox uses the ATI GPU, and then I think I can't remember. I think Xbox uses NVIDIA or vice versa. But it's a similar hardware to what you use in the PC, but the driver and API are vastly different. But because it is the same level hardware, the same level of consideration for one hardware will likely transfer to another. This is why a lot of people are doing optimization in shader. They will be just like larger company tend to have actually a whole team dedicated towards optimizing that as well. Our great friend Hambo, who I initially wanted to get to give this talk, told me in great lengths on how people basically been bothering with different company coming and bothering his work on compilers. Like, hey, we want to do this very specific thing, but it's very slow. Because look at the bytecode it generates, and it's too slow for the GPU, and he has to go and fix all that. According to him, the most annoying people was Activision, because Call of Duty is always one of the bigger titles, and that's also like it's interesting corporate dynamics, right? Like I bet you didn't know that. Like, if you are running, if you're making one of the top selling video game, you get direct support, and you can actually change how the compiler works at Microsoft.
Oh wow.
Yeah.
I think that applies to other consoles as well. If
Absolutely.
you're big enough, yeah.
Absolutely. Like, if you, it's very much like if you get big enough and then you get to sway the market, then you have a lot to say on how other people conduct their business.
Right.
Where can we learn more about GPU groups and stuff like that, and how locality works under the hood?
So-
Or can you do a line on that too?
That's much tougher, but I would say in general, if you to use like cache-friendly data, it's gonna help CPU and it's going to help GPU, right? So the way to kind of see GPU, like GPU used to be a lot more different than CPU, but lately they are, I would say, like, architecturally they are convergent, right? Used to be that GPU doesn't really have branching. So what it does is when you have one shader, you actually execute both branches, and then kind of do a linear combination of the two branches to give you a result. That's how GPU used to implement if statements. If you could believe that, it actually runs the branches. But lately, GPU is getting smarter, and then it has local branch prediction. So you can basically treat GPU as a very slow CPU, but has like 4,000 cores. Right. So all the cache locality comparison, they're still applicable. The only difference, I guess, is that in CPU you have to worry about cache coherency, right? Like because if the two GPU cores are fighting for the same, writing to the same resources, they actually end up having to wait for the cache lock to sync up. But for GPU, that's not really a consideration because GPU doesn't really have a data lock. It just everybody writes to everything all at once. An example, so basically, so the general principle to apply is that are you making sure that you are compacting your data, right? Like, are you using a structured array as an array of structs? That's actually a common thing that people often miss. Like, for example, if you're storing all the information like position and color, and then so okay, here, imagine if your data looks like this. So you have the color, you have the precision, and you have like health, HP, MP. Let's say I'm going to talk, for example, you're doing a mass like scale simulation, like huge amount of characters on screen, and then you are running some simulation, right? And then if your data is a array of structs, then it can look like this, right? So like this is 0 position, 1 position, 2 position, so on and so forth. And then up here you have like, let's say it's like each of this like 100 bytes long, and then the next time you see color will be like 101. So imagine if the operation was to like, okay, damage all the NPC by like 1 HP, right? Then it has to do all the page swapping, right? Because it's hitting like the second memory and 102 seconds. And then when a GPU is fetching memory, it kind of just fetches, try to fetch in the block as possible. So you're actually bringing all the data in. That's not necessary. So what you want to do is layer your data so that you have all the color in one array, and then you have all the HP in one array. This applies to CPU, by the way. It's actually very much CPU prefer this as well if you try to do mass operation. And it's GPU more or less just need to load this part. And then it's going to do a lot more efficient with it. Like grab all the data, runs that operation, and boom, and spits back out. So yeah, like there's a lot more deeper thing you can do. But just like if you just look at your code and try to visualize how your hardware is accessing those data, it is pretty much good enough to get you 90% of the way there. I don't know if that answers your question. I understand it's difficult to systematically study this because most people do run into this problem, and it's not really an academic interest. It's not really of academic interest either because it's very much an engineering problem.
Yeah.
Is this like a difference between object-oriented and the data-oriented approach you're talking about?
Yes, very much so. Like if you want to do make your data and program GPU efficient, it needs to be data oriented. In fact, like GPU forces your data to be aligned, right? Like if you try to put an array into GPU, like it will complain that like you just cannot have uneven data, right? If you try to draw a texture and then all the pixel is gonna have 8 bytes or 24 bytes, you actually specify the texture's format before you even put anything up there.
Interesting.
It is.
I'm actually working on a factory-like game in the side, and then this is actually what will really help. Really helpful.
Yeah, if you do any sort of factory game, which we plan to as well for our second game,
yeah,
you need to learn about data-oriented programming.
Yeah.
I also have some more additional research to share after this talk. That goes deeper into how what kind of intuition people use to optimize their program for data access.
Do we want to have another lunch and learn on specifically on this topic? I think it's like after learning about this, I think it's in a lot of ways we need to kind of like go back to our projects and kind of like rethink in like ways of cache locality, maybe.
Yeah, that would be a good proposal. However, I don't really have time for that.
Okay.
That if anybody want to volunteer to do a data-oriented programming, the best way to do it is actually just show benchmarks, right? Like, you want to show people like here's how you structure data, and here's how structure, and here's the operation you're doing, and look at the difference it takes, right? Like data is something like I think it's very interesting if anybody wants to volunteer to do that and discuss some common approaches to this. Any comments from the artist? Any cool effects that you guys want to do?
I actually talked to Window about something. Like we are trying to make the King's ship into a hologram projection, and it's like I don't know. Window said something about like making a shader about it, showing like the wireframe or something.
Could you show some references?
I don't have it right now. Like just imagine the Star Wall. Like they're like communicating like with a projection figure.
I did that. I have that, dude.
Yeah, but are you able to apply it on anything? Like for example, the King's ship. We do have the mesh for it.
If it has a mesh, we can do it. Here's if you remember, we had a dance.
Yeah, I do remember this one. I just don't know if we can use it because the King's ship is like more, not so much an organic ship.
Organic things are always harder to do. So if you have a non-organic,
I know, but
it's actually easier.
But we're trying to do the more like a wireframe of the model.
It's hard for me to visualize.
Let me take a look. Wireframe hologram bishop.
Oh.
Okay.
I mean, what's like the grid on the surface?
So something like this, probably.
Oh yeah, I tried to do something similar.
Right.
Is it the wireframe thing is actually?
So yeah, something like that.
Interesting.
Oh.
Interesting.
Okay, how would I go about rendering this in real?
Do you think this is a shader or just a model?
I think we need that for this.
We can probably make a shader out of it, but it's probably easier to make a model like have individual edge lines. Yeah,
right.
This is interesting. Where do you want it?
For the probably inside of some sort of King's office or inside of the spaceship itself, in the control room to show like the condition of the ship.
Cool.
So like something like that. So like there's a control room inside of the King's ship, right?
Here's what I recommend you like
Okay.
a VFS graph demo. If you yeah, like look at what's here. Everything here is made officially by Unity, and this is actually the old logo.
Uh-huh.
Yeah, and anything you see in this demo, like we can make it. Let me actually turn on sound because I think the sound is cool.
Chucker Rabbit.
I hope you made it safely down there. I'll make it. Can you hear me?
That.
Yep. That's very close to what we
Safely
want.
down there. I hope you can hear me. I can't hear anything. The whole system's busted.
VFS graph, which is a full type of computing. Yes.
So that's it. And that it is a shader.
Do artists have like a million shaders in their library where they're like, oh, we want this effect here. Oh yeah, I did that. Let me just throw that on.
I see you in the monitor.
Security check in progress.
Good to see you well.
To run and build. Usually people sell like a VFS pack.
Access granted.
But my approach has always been I'm gonna try to make it myself because usually all the control was concerned. But yeah, I believe there are people who make living.
There's a secure shell terminal there, just where you are. Put in the coordinates and get us to the landing site. You have to get us out of here now.
Effect I want on my actor game.
Select landing target.
I feel I've seen all of these in all the sci-fi movies or TV shows.
Yeah, but now we're doing it in real time, which is actually quite a feat.
There it is. Hurry up, we don't have much time.
Actually, that leads me to another question. In movies, do they use
Landing
a similar
target located.
thing to achieve the graphic?
Good question. It used to be that no, they used to
Attention.
have like, offline render.
Multiple
but
weapon
lately,
signatures
more
detected.
VFX software has been
Incoming.
showing real-time preview mode and a better version
Shield
of
taking damage.
like,
Warning.
so they will use the
Power
real-time
down to
visualize
32%.
how it look, and then
Substantial damage to shield. Power down to 17%.
whatever.
Core energy depleted. Shield power down to 9%.
I'm sorry, Veer. I'm sorry.
There's also
Warning.
the idea of virtual production.
Shield has been deactivated.
Just they can find a
Immediate evacuation. Proceed to the tenders now.
But yeah, I'll send you this video, Hakia. If you want anything, you can wishlist.
Yeah, basically just the pipe effect over this.
Alright.
Mhm.
Cool. And so what? There's a Mandalorian. Anybody seen that show? I can't spell that for shit. Oh my god.
Yes. Mandalorian. Baby Yoda.
With Baby Yoda, yeah.
So yeah, I mean, here's another. So Mandalorian is basically uses
Part of what's been fun about
Neo
collaborating
technology.
on The Mandalorian with Lucasfilm and Disney is that we have been able to see through a few technical innovations and a few firsts
That's
that I think
happy,
are going
right?
to have a lot of impact on the way television and movies are made moving forward. In partnership
From
with
Iron Man, yeah.
ILM
Yeah.
and Epic,
Happy
we
Iron
have
Man.
put together a system whereby which we can have game engine, real-time render, and video wall technology coming together to create a backdrop for the big, beautiful world of
Yeah,
Star
shaders
Wars.
like magic.
The volume is 21 feet tall.
You
It's
can
75
build entire
feet in
games with-
diameter, run by 7 machines, pumping the visuals onto the screen that's being
They
created.
actually built it.
They basically have
on the
giant
screen
like
within
screens that
24 hours
displays
of being
the
final.
render result from Unreal Engine in real time, and that's how they create a
When you
set.
first walk out there, because it completely surrounds your peripheral
It's a
vision.
completely different
And you
world now.
Really quickly forget.
No more green
that
screen.
How
you're
many-
indoors. And
How
you're
many
not out
GPUs do they have to
because
render
it
these?
feels like a real
Not
three-dimensional
that many.
environment surrounding
It's
you
like
because it
Unreal
is a
Engine is pretty
three-dimensional
efficient.
environment.
you can allow
You probably have
your
one like
key
a good,
creatives
probably
to
like
all make
6 or 7
decisions
machines
together,
because they have a lot of
so that
video
the
walls.
shots are captured entirely in camera, which allows for a better performance.
And what was so exciting about this is by bringing
I'm
those people
imagining
together,
it's going to be
things
easier for
started
them
to click,
go to a
and
place
we
that
started
look
to
like
realize,
that and
well,
then
let's not just do green
record
screen
and
interactive
then
light.
put them back.
If we're going to design the whole
As
set
a
and
backdrop.
game engine,
Yeah,
ahead
they
of
do that,
time,
right?
maybe
There's
we could have
so many ways
some
they can
camera sets.
create the backdrop. They can capture in real time or they suggest, right? It's the same problem
Yeah.
that we use.
background that we can
face.
directly
So that's what I'm
photograph.
saying, like
So
thinking like
we
mine
end up
could be
with
used for
real-time
film as well.
final pixels in camera.
If you look at visual effects heavy films, you've got a
Like,
film set
and we have
and
this
it's gonna
like
go
a
to
camera,
post,
like
it's
then
gonna
depending on
go
the
put in.
position of the
Here
camera,
we're
it
putting all
renders
at the same
that
time,
in
and
that
we
pretty
create
viewport.
a background and foreground that live together on the volume harmoniously.
When we started to play with the idea of using Unreal Engine for virtual production, that's one of the things that Richard and John started to embrace, is that you've got this very dynamic world where you can have randomization of things and find the happy accident that gives you the perfect shot. Being able to see the actors point at things and see what they're looking at was pretty transformative. It gave everybody context, with the added benefit that if you want to move a mountain from there to there, you can do it instantly.
You could switch between the Iceland location to the desert location, all within the same day of shooting.
Another channel.
That's another
the
big
ability to shoot
cost reduction, right?
10-hour dawn
People don't have to go outside
is
anymore, right?
extraordinary. To
Same
shoot
location, film
any
all the possible
sequence
shots.
where you
This is the
say,
future.
oh, this world's not quite right, let's just move it a little bit. An extraordinary number of benefits and advantages for shooting in that environment. It's mind-blowing what that tool is.
What you see is really what you get. And that's
And they
something
can
that
solve
really
the
means
lighting
a lot
issue
to
once and for all.
filmmakers,
Yep,
especially
yep.
those-
It
You have
monitors
literally
the,
like
yeah.
real environment light projected characters.
Shots of character in a vehicle traveling through a complex
It's gonna be natural
environment.
light.
It's always very
Like, no need to mock.
Yep. Stage.
Not gonna lie, that's pretty dope.
Like actual
What you're
HDR.
doing is you're taking this
Ha,
technique
you guys
of,
have no idea how
image-based
much
lighting
time I
that we
spent
use in
on
computer
putting
graphics.
up the lighting for my
Here, we're gonna use
vlog.
it to light a subject.
And then we would
You
do
think you'll
shoots
rent
where
the
we
studio
would
to,
texture
film
map
your vlog?
real lit surfaces onto our
Yeah.
Game Engine Geo, and so the camera could move anywhere. We would do interiors, like Werner Herzog's office. And then you started doing things like building sets into it, having half a spaceship with reflective surfaces. And so it became exciting because by the end of the season, it was like, let's start designing sets around what this could do well.
Just like the good old days.
With Star Wars, we're building on a rich legacy of innovation, and getting to partner with Jon Favreau to make his ambitious vision a reality, it's really a game changer for filmmaking.
Game changer, get it? Because Unreal Engine is a game engine. Alright, hope you guys had fun. It's been an hour. I think we'll do something more lighthearted